All righty. Hello out there. Anyone home?
Hello,
Good.
Professor.
All righty. That's tremendous. Okay. So glad we can all hear me. So let's get to today's agenda here. Let's bring up some notes. And all right. We have 3 sections left. And then we're done. I'm going to basically do a section and a half this week, and then same thing next week. There's a good place to split it up in 9.2. So I'll have to make sure when I post this, I put an announcement. Hey, it's not an error in the recording. It's not. We did stop part of the way. Well, I'll say that whenever we stop anyway, so people will be able to hear me say that. So, okay, let's get screen share going here. So let's see. Hopefully you're looking at my notes for intro to hypothesis testing. All right. And also I promised, I think, that I'd talk a little bit at the end of class, because we'll have time tonight, about that assignment thing, or that Excel assignment. I was kind of run through some of the highlights on it. All right, let's see. Now this hypothesis testing is it's another part of inferential statistics, like confidence intervals. Except the difference here is, instead of trying to place the population parameter, in our case we're only dealing with a mean, but in more advanced studies you could study proportions and standard deviation and variance and stuff, but ours is only the mean for this class. So instead of trying to place it in an interval with a certain probability, which is what we did with confidence intervals, we're now going to actually compare it to a specific value and decide if we have the evidence to, refute that claim or not. So let's say, I think that the average, score for some standardized exam or something is, whatever, I'll just make up a number, 400.
Okay.
And we'll say, we'll test if we think, then we'll use sample data to decide whether or not, we're not absolutely proving anything, but we're, deciding if we have a statistical valid, argument, in other words. Just like confidence intervals, you're not proving anything with those, but you are, with a high degree of probability, is that the mean would be in the interval that you created. Now, I will tell you that this will be a little more challenging than confidence intervals. Not mathematically, conceptually. Nothing mathematically in this class is overly difficult. It's a little trickier, because confidence intervals sort of had the same format. It just depends on whether it was a Z or a T. That was really the only challenge. And, you do blah, 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 you margin of error, and you have the interval. It's created the same way every single time. Well, now we've got to read these problems, and we have to identify if they're looking for greater than, less than, equal, not equal, stuff like that. That's where the challenge kind of comes in on this. All right, so I think we're up for a good challenge, aren't we? I'm not trying to scare you or anything, but just pointing out the evidence here and the facts. Does require a little more thinking. Now, each hypothesis test has a pair of statements that always go together. They work together as a pair. You have 2 of them. We have what's called the null hypothesis, alternative hypothesis. And sometimes the alternative might be HA or H1, just depends on what book. And then this H sub 0 or whatever. I often just call it HO for simplicity. But anyway, the null hypothesis, the HO, is always going to be a statement of equality. It's going to contain either less than or equal, equal, or greater than or equal. The alternative will be the symbol that's the opposite of the HO, and it will not include equality. So for example, the less than or equal to, the opposite of that would be greater than. For equal, the opposite will be not equal. And then for greater than or equal to, the opposite will be less than. Complement in this case meaning the opposite of, but they do kind of work together. So anytime that we have an hypothesis statement, it's going to look like one of these forms right here. Now the mu sub 0 is going to be whatever numerical value we're testing against. The mu on the left is just, it's always there. So in other words, you're saying the probability, the null hypothesis is the mean is greater than or equal to some number. So the mu on the left is always there as a symbol. Mu 0 is whatever number we're testing against. So they have to look like this. Less than or equal to is always a HO, pairs up, greater than or equal to pairs up with less than. Less than or equal to pairs up with greater than. So, and then equal pairs up with not equal. Sometimes, in an exam, I might have, which of the following is correct or not correct. But if you ever saw, just say, I'll write one of many. I think that might come up in the homework somewhere too. Maybe not this week's, might be next week's. But anyway, I may look for it. But so if you ever saw something written like this, I think there might be one where you have to pick the right hypothesis statement so you can rule out which ones are obviously wrong. So let's say if I ever had one, I'll just put a number here, 10. And then I'll write it like that. That right there is 100% wrong. It could never be written that way. Even though the symbols are going in the right logical direction, they're going opposite. The HO has to have the equal. And the HA will not have the equal. So that is automatically an invalid hypothesis statement right there. It should have been this, like that, to be correct. So if it was written like this, then that would be acceptable. Now, of course, then again, it still has to be correct for whatever problem you're trying to solve. I'm just speaking purely in terms of what is a logical possible statement, in other words. So the HOs, you always have those there to refer to. So, it's not saying you have to memorize these, but you do have to realize that, you have to get them, and it's always going to be one of those three. That's it. Those three right there. Those are our three key pairs. All right, so I'm going to go ahead and erase this. Now, when we start looking at hypothesis, word type problems here, all they have to do in a word problem is give us enough information to determine one of these two, the HO or the HA. Because since they have to work in these specific pairs, if you know one of them, then the other one has to be whatever it has to be one of these three pairs. Now we call that the claim. Now sometimes the claim may be the HO or the claim may be the HA. And what determines that is what symbol goes with the wording of the problem. If the symbol is going to translates to greater than or equal to, less than or equal to, or equal, we know that will be the HO. If it's less than, greater than, not equal, we know that will be the HA. It would have to be. That's how we'll know which is which. But you only need one of the two, and they automatically pair up like this. This will be a lot more fun when we put this in action here shortly. There's a lot more background to this than there is confidence intervals. In fact, this whole first section is mostly terminology and setting up the logic of the process before we really do much we'll do some calculations in the next section. That might be a little bit this when we use the normal curve at the end of this one, but anyway. Okay, that's basically saying what I just said right there in the block. So here's some wording. I don't like to get too tricky on the wording. I'm not out. I don't know. We'll have to see how ridiculous maybe if the homework gets or whatever. But I guarantee you on an exam question, I don't like to make these too tricky. So if you see phrases like is or of also, they both mean equal. So I claim that the mean whatever, we have a mean of something. That's the same thing as saying mean equal. Is not, differs or differs from, or just differs, that's fine. That's not equal. At least or not less than, more likely we would see at least, but I want to include not less than. That's greater than or equal to. Fewer than, less than, that's just less than. No more than or at most, those are both equivalent ways to saying less than or equal. And then more than, above, I could have put greater than, either same, obviously that's the same thing. More than, greater than, or above, that would just be a greater than symbol. Okay. All right. Okay, let's see. We're going to read this statement, and then we'll set up the ho and the ha, and then we'll just identify just which one happened to be the claim. Like I told you, the claim could be the ho or the ha. It all depends on what symbol the claim produces. Consumer analyst reports that the mean life of a certain type of automobile battery is 74 months. Okay. Is means equal. Equal is automatically a ho. And then it pairs up with not equal. So here's what we'd have. We'd have the mu equals 74, mu not equal 74, and I'm labeling that as the claim because that was given right here. Now, the only difference is, let's say if this would have said, we claim that the automobile battery is not 74 months. Not 74 months. The ho and the ha would have been exactly the same, but I would have labeled the ha as the claim because it would have been telling us not equal in the wording of the question right here. That's the only difference. But structurally, it would have worked exactly the same. We've been doing a hypothesis test on this, which we will be doing. It wouldn't have made any difference. It's just labeling. So it doesn't matter. It doesn't mean, in other words, if you say is not, that doesn't mean that becomes the ho. No, is not equal always has to be the alternative, the ha. Company claims that its brands have mean paint drying time of less than 45 minutes. Okay, less than. That's what I mean. It's pretty straightforward. Less than is alternative, a ha. It pairs up, I'm not going to scroll back up the page there, but you'll be able to look whenever you need to. It pairs up with greater than or equal to. They're opposites. But see, notice the claim this time, because the claim told us less than. So this time I have the ha as the claims. That's what I mean. The claim is determined by what symbol it produces. It could be either the ho or the ha. That's irrelevant. It's by what symbol the wording produces. And like I said, they only have to give you one out of these two statements because the other one has to be the one that partners up with it. So less than pairs up with greater than or equal to. And here's another one. Claim the mean NBA score for all games in a season was more than 100 points per game. More than's greater than. Greater than is a ha. It pairs up with less than or equal to. And it was also the claim was more than, so it would have been also the ha, and it pairs up with less than or equal. All righty. Hope we're doing okay so far here. I'm always at a little bit of a disadvantage sometimes with these kind of things versus being in class. I can sort of look at people's faces and see if they look dazed and confused or not. So hard to tell, but we'll keep plugging along. All right. Now, types of errors and level of significance. Now, when we perform a hypothesis test, we reach one of the following two conclusions, and it's based on the null hypothesis. We either reject the null hypothesis or we fail to reject the null hypothesis. That means we either reject the hoe or we fail to reject the hoe. Now, here's a common misconception. I'm going to go ahead and explain it right now. Number two, you might think failing to reject the null hypothesis is the exact same thing as accepting the null hypothesis. And that is not correct. They're not the same thing. Kind of close, but they're not the same thing. Because the idea is, if you reject the null hypothesis, you feel like your data that you have is really strong and you can reject it in favor of the alternative. Failing to reject, that just means, okay, we don't have we may not agree with the null hypothesis, but we don't have the evidence strong enough to reject the hoe. That's what we're saying. And I'm going to give you an example of that here in just a minute. That's not even a numerical example. We're going to use a criminal type, thing here to use sort of as a non-numerical example of the idea. So failing to reject is just not the same thing as accepting. So a lot of times a statistician, they'll set this, if they think they want the alternative, they'll set it up to where if they want the alternative to be true, now they still have to rely on the data, they'll set it up to where they're hoping for a reject, because statistically that's a much stronger statement. If you can reject it in favor of the alternative, you're much more confident in your results. All righty. Now let's look at these errors here. Now when we say errors, we don't mean human errors here, not like mistakes. Give you an example. The only type of error we had for a confidence interval, if you do, like say, for example, a 95% confidence interval, that means there's a 5% chance that your mean was not in the interval. That's what we mean by an error. Process error. It doesn't mean you did anything wrong. It just means the particular sample of data you collected and to calculate your confidence interval just happened to not contain the mean. So the same thing here. These are not errors that you make. These are more like process errors, but they're a little more sophisticated than just a confidence interval. That's what I was talking about. They're just a little more challenging in the way it's sort of worded and stuff. Anyway, a type 1 error occurs if we reject the null hypothesis when it was true. Now, I said all this, you're not going to know whether it was really true, but we're just saying this is what the error would be. And it makes sense that it would be an error, obviously, right? If you rejected the hoe and the hoe was true, that would be a mistake. And then the other type of error you could make is a type 2 error. Yeah, all books use Roman numerals for these. It's pretty consistent. Is if you fail to reject the null hypothesis and the null hypothesis was false. Okay, I think that makes sense why that would be an error, right? You did not reject the hoe, and it turned out the hoe was wrong. So obviously that's a mistake. Now, we're not worried about this type 2 error and the beta. Now, these are Greek letters, by the way, alpha and beta. We are going to be using this little alpha symbol here in just a minute. Okay. So what they're saying, type 1 error here is a false alarm. And I don't ask those questions on test here. And then type 2 error is often referred as a missed opportunity to maybe take some corrective action or something like that. If it was something you could take corrective action on, or whatever. But, okay. I just made this little chart up right here. So And these are all not equally likely outcomes, by the way, either. We'll talk about these errors here in a minute. But so let's say if you did not reject the hoe and the hoe was true, that would be correct. That makes sense, doesn't it? Yeah, you don't want to reject it if it's correct. The next type of situation is rejecting the hoe if the hoe is true. That's what we just learned was a type 1 error. I'll come over here, second column. Do not reject the hoe when the hoe is false. That's a type 2 error. And then you reject the hoe if the hoe is false is correct. All right, the level of significance is the maximum allowable probability of making a type 1 error. Okay, so this is a small number, thank goodness, and we use this Greek letter alpha, so just because sometimes a problem might just give you, okay, alpha equals 0.05, so we should just realize that's going to be an important number to determine our rejection or not. These are just common values of alpha. So they're low probabilities of making a type 1 error, which is good. You know, this would not be a very good process, for example, if you had a 50% chance, for example, of making a type 1 error. You know, it's kind of like you might as well flip a coin at that point. But so they're low numbers here. So, okay, here's the criminal kind of justice system example that I wanted to use to point out while failing to reject the hoe is not the same as accepting the hoe. That's one thing I miss, but another thing I miss about doing this particular thing face to face. I like to look at people's reaction the first time I start calling it hoe. I like to look at their faces and see how they react, how people react. Some laugh, some are kind of shocked. I don't know. Anyway, I don't have the advantage of looking at you. Well, I guess I could bring people on there, but I'm not going to. You know, you have every right to be sitting at home in your PJs while taking this class. So this is not like a business meeting or anything where you have to be dressed. All right. Now, the idea, the theory behind the criminal justice system is supposed to be the null hypothesis, the defendant is innocent, and the alternative is, I don't have that number there for it. I always use an example there, is they're supposed to be guilty. So it's up to the prosecution to try to present evidence to reject that innocence in favor of guilt. Now before I talk about these errors here, think about how this works. You know, you can kind of watch any kind of legal show on TV or whatever. You don't have to be a lawyer for this. You know, they talk about when they read the verdict as either not guilty or guilty. But when you say not guilty, that doesn't 100% mean you think that the person is innocent. Now, from the defendant's point of view, they're free to go, obviously, so they don't care. Doesn't matter to them personally. But it doesn't mean you 100% think that they're innocent. It just means that you did not have the evidence to reject their innocence, in other words. So when you say not guilty, that doesn't mean you're proudly proclaiming their innocence. I mean, unless some other evidence comes up that 100% proves they're innocent. I'm just talking about in general. In general, it doesn't mean you're 100% on board with their innocent. There's just not enough evidence to declare them guilty. So that's what I mean about, you know, this, you don't necessarily 100% accept this, but you don't, you know, say it's wrong either unless the evidence is there. So, yeah. So you fail to reject the null hypothesis means you declare them not guilty. Type 1 error would be rejecting their innocence and finding them guilty. And then a type 2 error is you fail to reject the null hypothesis when the alternative hypothesis is true. Yeah, I don't expect you to know all these theories by definition, but you fail to reject it when it was false. So that in this case, in this context, it means type 1 means an innocent person is found guilty, and type 2 means a guilty person was found not guilty. And, you know, I'm not trying to start a big debate here or anything, but I think it's pretty safe to say that the type 1 error in this particular situation is far worse. You don't want an innocent person found guilty. You know, the occasional guilty person will get away with it. But so, yeah, that's by far the more. So as far as, you know, which error is worse, you know, sometimes it depends on the situation. There are some where the type 2 error could be worse, but not in this scenario, not in this example. All right. All right, let's see. Now, here's where, like I said, we got to really start thinking here a little bit. I guess I can save all that. Yeah, okay. Well, I might do that again if I need to, but I did a bunch of stuff here. I saved by mistake. Your notes might look like this, I guess. I don't know. Maybe not. I hope not. All right. We have a pair of hypothesis statements. Like I told you earlier, you know, some whether you see H1 or HA, same thing. Less than or equal to 47. I get these examples from different test banks, stuff like that. So it just depends on, you know, what book went with it or whatever. And then, of course, if we know less than or equal to 47, we didn't even have to be told this one because they work in those pairs we talked about earlier. That means greater than 47. Now, what will result if we conclude that the mean is greater than 47? So let's talk about what that means. Whether, you know, as far as rejecting the hoe or not rejecting the hoe. Okay. If we conclude that the mean is greater than 47, we would have to have rejected the hoe. In other words, when we forget this, I'll come to the 52 part. So that means we rejected the hoe if we thought the mean was greater than 47. All right, now here's the part that's just kind of magic right here. You wouldn't have any way to know this in theory. But then suppose, all right, by some miracle or some whatever reason, we found out that it actually was 52. So we're trying to decide, there's three things here. We either made a correct decision, we made a type 1 error, or we made a type 2 error. Now here's where I label this rejecting. This is important, because one thing, it kind of eliminates an answer already. Let me go back and look at these definitions right there for the type 1 and type 2. Notice that the type 1 error is based on rejecting the null hypothesis. So this answer has the potential to be a type 1 error. But notice a type 2 error is based on failing to reject, incorrectly failing to reject, but in other words, fail to reject. So since we rejected, that means that automatically, this none of the above would never be on a test. It's going to be one of those three choices. So this is gone anyway, because this will never have this. But what I'm saying is, because of reject, this is automatically gone. There's no chance it's a type 2 error. It either has to be a correct decision or a type 1 error. So here's where that 52 comes into play. Suppose it is 52. That means it was greater than 47, right? So if it was greater than 47, I think that indicates that the null hypothesis was correctly rejected. Therefore, A, we've made a correct decision, is the correct answer. Now, suppose I just change one thing in this question. Suppose everything's the same, but instead of 52, we've got 42. In other words, we still rejected the hoe, a mean greater than 47, but then suppose by some magic we found out that the mean was actually 42. I think it would have been wrong to reject that hoe, wouldn't it? Because 42 belongs to less than or equal to 47. That would have been a mistake. So in other words, the hoe was true. 42 is less than or equal to 47. So if we rejected the hoe when the hoe was true, we would have made a type 1 error. See what I mean about how you really have to kind of think through this? But there's no chance that this problem would have been a type 2 error. Now, other ones can be, of course, but not this one. Let's take a look at the next one. Okay, no more than 9.1 hours. No more than is the same thing as less than or equal to. So they got our hoe and ha set up. Less than or equal to 9.1. And then the opposite's greater than 9.1. Now, this one didn't give us a specific number, like the 52 that we had in the last one, but it gave us some good information right here. That's good enough. This is the same as the last one, that we are rejecting the null hypothesis. So, yeah, this is more like what the answer choice would look like on a test here. It wouldn't have that none of the above nonsense. One of these days, I think I'll get rid of that out of the notes. So this is gone. It's either A or C. I would change the wording on this a little bit, where it says it's okay, but it says where it has not increased. I would probably actually say, in fact, that the mean running time is not, greater than 9.1. But that's still okay. The point is, not increased is still good enough. That means it's still less than or equal to 9.1. So we rejected the hoe when it was true. It's still less than or equal to 9.1. So there's our type 1 error right there. Ta-da! Let's see. Okay, SAT scores, blah, 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 blah. Just kind of blah, blah on down till we get to the ho and ha part here. Equal, not equal. All righty. Non-rejection of the null hypothesis. Non-rejection, failing to reject. See, if you have reject or fail to reject, those can both lead to the correct decision. They just can't lead to the wrong error. So failing to reject the null hypothesis now means type 1 error cannot be the answer, because type 1 is based on reject. But correct can still be the answer. Correct can always be the answer. Doesn't mean it'll always be the answer, but it can be. But when it says reject, you can eliminate type 2. When it says fail to reject, you can eliminate type 1. Then you have to decide which one of these is correct from the rest of the information. Now, not equal just means differs from, so different. So we don't mean it has to increase or decrease. It's just not 500. So the scores changed. They're changed. So whether they're above or below, we're just saying they're not 500 anymore. So we failed to reject the hoe when the hoe was false. It means the scores have changed and we did not reject. So therefore, that is definitely a type 2 error. Beautiful. All righty. Statistical tests and p-values. Okay, a test statistic. That's something we're going to see a little later today. It's a calculation using mean, standard deviation, and hypothesized mean, and we're going to come up with a numerical value. It's a pretty easy calculation. Calculator, just program that can do it for you too, but it's not hard. It's a numerical value that we're going to use. And now the definition, I always have a tough time explaining the p-value, but that's okay as long as you, the conceptual definition of it's tricky, but understanding what it is and where it occurs is not difficult really. But so I'll just go ahead and go with this definition and not worry too much about it. The p-value of the hypothesis test is the probability of how likely the sample results are true. The smaller the p-value implies the sample results are less likely to be true. Well, you're going to be able to get p-value, well, from technology, so you don't have to really worry about it too much, but I want to look at it using the normal curve. It's going to come from the normal curve also for people that are needing to do it that way. All right, so this, you don't have to get too bogged down in this definition. But yeah, the p-value is going to relate to the test statistic. Now those three basic hypothesis statements that I gave you at the beginning now have names. Nothing too fancy, but they have names. The one that represents the hoe of greater than or equal to and the alternative of less than, that is called a left-tailed test. That means when you calculate your test statistic, it's going to be a Z. We'll also have T's, but not today. It'll be a negative. It'll be something that's a negative number for that test statistic. And the p-value is just going, the actual value is going to be the area on the normal curve to the left of that test statistic. So it's not hard to come up with conceptually how to get the p-value and calculation-wise, even if the concept's a little bit weird. But it's that area to the left of the test statistic, because the test statistic will be negative. Now the next one, where you have the ho and ha of less than or equal to paired up with greater than, that is called a right-tailed test. The test statistic will be positive, and the p-value will be the area to the normal on the normal curve to the right of that test statistic. Which, of course, if somebody using the normal curve can do this very easily from what we've learned before and how to read the normal curve, is all you got to do is flip the test statistic over and make it negative, and then look up the chart value, and that'll be the answer. Now, the next one's the trickiest one. Equal, not equals, is called a two-tailed test, because to be, the other one's, less than for the ha meant goes to the left, greater than for the ha goes to the right. But remember, equal can be represented. If you say something is not equal to something, it can be not equal by being either smaller or larger than that value. It's not one direction. In other words, it's two directions. And then for this one, the test statistic may be negative or may be positive. And because it's representing both ends, and each shaded area is actually half the p-value. So added together, they make the entire p-value. Now, the way I sort of explain it here, then, we'll incorporate technology into this, but if people that are doing it using the chart, is all you really have to do is whether the p-value is negative or, the test statistic, whether it's negative or positive, you just look it up as a negative on the chart, you get that number, and then you get that area and you multiply the area by 2, not the Z value, and you multiply it by 2. I won't bring up the normal curve. I'll show you kind of a calculator way to do this. you can use normal CDF. I don't know, but for this one though, it might be just quick just to look it up. Really, I mean, you can decide if it's worth using normal CDF, but I think you know how to read the chart already. So, so let's say it's a two-tailed test. The Z is 2.34. So it could have been negative or positive. It didn't matter. I would have done this the exact same way. If it's negative, I just would have looked it up as negative. If it's positive, I'm making it negative. So you would look at, I just shaded both ends here because technically the p-value does represent both regions, even though the red number is the actual test statistic. But my point is the answer would have been exactly the same in this problem, whether it was negative 2.34 or positive 2.34. So I would look up negative 2.34 on the chart. I would get 0.0096, and then I would multiply that by 2. The two-tailed test is the only time we multiply it by 2, not for the left or right-tailed. The left or right-tailed, you get it just right off the chart. So I don't know if you would find this easier. Let's see. Than just using the chart, because you can do normal CDF. I've already got the negative infinity there, but you still need to put the negative in here. Negative 2.34, because we want to cover, yeah, you don't want to go positive because that would have covered the wrong. But then you got to double it. So I don't know. It's up to you. This way or the chart for these. Now, when we start having sample data, we're going to have a program that's going to do the p-value for you. But I've been known to ask a question like this on the exam 3. All right, so there we go. Now here's just, I guess I could have put these problems in a little bit earlier there, but now it's just identifying whether it's called left-tailed, right-tailed, or two-tailed. Now we did those problems earlier where we set up the ho and the ha and identified the claims, but that was before we had named them left-tailed, right-tailed, two-tailed. Elmo claims the mean GPA for all UHD students is more than 2.9. Determine whether the hypothesis test is left-tailed, right-tailed, or two-tailed. So all you got to do then is just set up the correct ho and ha. Then you can look and see by definition which one it is, left-tailed, two-tailed. So it's not too bad. More than's pretty straightforward. So more than would have to be a ha. That was the claim also. Pairs up with less than or equal to. And then you go back up here, and there it is right there. That setup is known as right-tailed test. Yeah, so we're just taking it one step further than we were doing earlier. Lucy claims the mean GPA for all UHD students is 2.8. Determine whether left-tailed, right-tailed, or two-tailed. Is means equal. So this time the claim happened to be the ho. It pairs up with not equal. And that would be equal, not equal is always a two-tailed test. Oh, maybe I'll hit some of the highlights of this real quick, and if you want to read it in more detail later. Yeah, this is kind of what I was saying earlier about failing to reject this second sentence. However, failure to reject the null hypothesis is not proof that it's true. You can never prove the null hypothesis correct because the decision is based only on the sample information, not the entire population. In other words, if you fail to reject, you can only conclude that there's insufficient evidence to warrant its rejection. Now, one thing is yeah, like it says here in the first sentence, you know, when you do reject, that's not absolute proof the alternative is true, but it's strong, statistically solid evidence. Yeah, there is no absolute on this. but failing to reject the null hypothesis really accomplishes nothing. All right, let's just see. That's kind of what I was saying. Okay. Statements. That's why I put this in here. It's a good summary of terms and stuff here. Statement of the null always has an equal. Statement of the alternative always has something that's not an equal. Either just less than, greater than, or not equal. Okay, so all right, that's good. You might want to look at that when you get a chance. So, all right, let's see what we got here. That pretty much takes care of that. And let's I'll bring it up right here. Actually, yeah, let's open up the homework. All right. All right. Look, something got away from me there. Okay, here we go. Assignment manager. There we go. All right. Nine one, 9 2, 9 3. All right, we'll do one of these. Here's you can bring up my normal curve, or you can use the calculator, whatever we want here. But you got to be careful though that you don't want to do if you do the calculator in normal CDF, you don't use positive 1.38 here. Let me just put a little sketch up here. It did say two-tailed, and it said 1.38. Well, that does not mean to the left. That means the right of that, and then along with the left of negative 1.38. So you got two options. Look up negative 1.38 on the chart and then double it. Yeah, so if you look up positive 1.38, that would not be right. All righty, cumulative normal. And then, or you can do the normal CDF if you want, but just do it to negative 1.38 and then multiply that answer by 2. All right. Maybe I should have used the calculator since I didn't already have the chart up. Looks like they had a chart there. I could have just used theirs. Looks like they brought one up also. So it was negative 1.38, I think. Let me double check that. All right. Negative 1.38. All right, why am I getting this stupid spinning circle here? There we go. Be right there. Multiply that by 2, that'll be 1676. Hooray! How about that? Oh boy, you know what? This I had this. We'll be able to answer this like right after. I mean, the first thing I do in 9.2 will solve this. So I do. You know, we can come back to it, but I had this. Maybe I should start putting this back in 2.1. Actually, 9.1, but I had it in both. Actually, but it's kind of redundant, so it's not in. I don't think I had it at the bottom of my notes there, but it's not hard. It's just we'll see it here in just a few minutes. Here's another two-tail. I'd like to see a left or a right tail. Yeah, here's that legal system thing. I wouldn't mind you giving that one a whirl. Okay, this one's just got to be, yeah, innocent versus, yeah, that's right out of my notes. Let me see. I might come back to that one problem. Let me take a look. Oh, this is a good one. First of all, there's a whole lot of crap on here. First, anything that doesn't have both mu's there, you know, anything, all that beta and X bar and mu with X bar. I'm going to go through and eliminate everything that's wrong, first of all. Well, it's pretty much only going to leave one correct answer. Well, okay, let's read the statement first. All right. Set up the hypothesis test to prove the mean number of hours studied at your school is different from the reported 15.3 hour benchmark. All right, first of all, they got to both have mu's, so there's a bunch of garbage on there. So it's got to be either F or I. One of those is right and one of those is wrong. And it's all based on where the location of that equal and not equal have to be. F is wrong because the whole can't be not equal. I is correct because it has the whole as the equal and the alternative as the not equal. Excellent. Continue to see more. This might cover that other one then we can move on maybe, but let's see. What is a type 1 error for your test? Type 1 means rejecting the whole when the whole is true. And I don't expect you to already know that at the top of your head just from talking today. Obviously, you kind of need to go back and soak this up a little bit. But I'll just sort of say it's rejecting the whole when the whole is true. So it would be in something that involves rejecting the 15.3 when in actuality it was right. So let's see which one of these looks like it would model that one. I think it's A. In other words, the last part of that sentence where it says, when in fact it is not different, that's saying the whole is true. And we rejected it. In other words, we favored that it was different from that. Final check. They don't give us much room for error here, do they? But obviously it's so easy to answer that first one again. If somebody did miss this, you can get that first one answered in about 2 seconds. Type 2 error for your test. Type 2, yeah, I might just do this one. I might do one more, but then we might move on. I hate to have all your fun here. But I'd like for you to think on at least one of those other ones, think through the type 1 and type 2 yourself. Then you can come back to me if you're having issues. Type 2 means you fail to reject the hoe, and the hoe was wrong. And you did not reject it. It was a bad hoe, and we didn't reject it. All right. Failed. I like A for this one too. Concluding it's not different from the 15.3. So that means we concluded it was not different means, you know, we agreed that it was equal when in fact it really was different from 15.3. Fantastic. Wasn't that fun? I might just pop back here for a second, but like I said, I want you to take a shot at one of these. That was a good one to do though. I like that one. But I do want to show you, in fact, what I'll do is I'll leave this homework up, and as soon as after break, we will go and I'll go back and answer that one question that I told you is going to be the very beginning of this section. All right. Now, it'd be nice if I could move that problem. I probably can't do that. If I could move it over to the nice, oh well. Wonder if I could maybe add it there. It's too much trouble. Never mind. I need to do it. Remember to do it before the semester starts. But I think now's a good time for a break. We're going to have a short second half also here too. We're going to cover part way through 9.2. We're not covering the entire section. And that way we can save the rest of 9.2 and then 9.3 from next week. And we'll be done with new content. Pretty exciting, isn't it? So what do you say, about a 10-minute break here? All right. Welcome back to the show. Well, if the games continue here. All right. I already brought it up, these notes up, so. Okay, well, we spent that first section, you know, just going over a lot of this terminology, definitions, and, you know, kind of been teasing you a little bit. You're thinking, hey, I want to see some numbers. I want to see some calculations here or whatever, so. But like I say, there's just a lot more prep work to this idea than there was, you know, confidence intervals. You just kind of explain the basic idea, and then you can just jump right in there and start doing them. Just like we had for the confidence intervals, where we had to make the distinction between the Z and the T, same thing's going to happen here. So this section, which we're not going to finish today, is going to be Z, and then of course we're going to do still some of that Z next week, and then move over to the T. All righty, hypothesis testing for the mean population standard deviation is known. That's going to be the key here. Usually they're going to be larger samples also, but the main thing we're looking for is that the population standard deviation is known, sigma. All right, now this, as soon as we look at this, we can actually go back and answer that one homework problem. And I can go ahead and get rid of that section for now and bring up the new section. So let's look sort of the first way numerically how you can decide whether or not you're going to reject or fail to reject the hoe. And it has to do with this. I only briefly mentioned this alpha, which is the level of significance. That's going to be a value that's given to you in every problem. I mean, unless you're the statistician one day and you're choosing alpha for yourself. So decide whether or not to reject is you compare your p-value with the given level of alpha. If the p-value is less than or equal to alpha, then you reject the hoe. Very unlikely it'll be equal, but it technically. So if you say it is less than or greater than, probably okay. It's not impossible, but I don't think I've run across one where the p-value. Well, it is possible. And then if the p-value is greater than the alpha, then you fail to reject the null hypothesis. So when you're comparing these, make sure you kind of stay consistent. I would always do this. I would always put my p-value on the left and then my alpha on the right. For example, let's forget p-values and alphas for a second and just say we're comparing two numbers. And let's say put 6 greater than 2. And I'll put 2 less than 6. Is there anything logically wrong with either one of those statements? I don't think so. They're both accurate, aren't they? 6 is greater than 2 and 2 is less than 6. But you see, the problem is, if you wrote this the other order and you went by either greater than or less than, it could lead you to the wrong conclusion, even if you did it correctly. So in other words, yeah, I'm just trying to keep this as straightforward as possible, but I will mention that saying that the p-value, well, at the bottom, the p-value greater than alpha is the same thing as saying alpha is less than the p-value if you reversed it. But it's just that, but then again, it brings in the less than into play, and you might think reject would be the answer. So it's best that you put your p-value on the left and your alpha on the right so you don't get twisted up by that kind of inequality logic there or whatever. That's just a suggestion. Now let's go back to the homework question real quick. We can do that. I don't think there were any. Yeah, there were no calculations on that one. It was just all right. It was about the third or fourth one, I think. What I thought. Wait. Oh, second one. Yeah. So this is good. We take this one, and I'll come back to my p-values 0.0212. Yeah, this is an excellent question, but it probably should have been in the next section, unless I just go back and redo the notes or something. But okay, so that's your p-value. Your alpha, was it 0.09 or 0.0? 0.09. Your level of significance, that's your alpha. Same thing. And let's figure out what symbol goes in there. You don't have to worry about the equal here, like I said. If you just wrote this, that's fine for this. A little different when you're setting up hoes and ha's. So I think we can say that 0.0212 is less than 0.09. Okay. And let's go back and see what that says. P-value less than alpha, then you reject that hoe. P-value is less than alpha, reject the hoe. Okay. Ta-da! Yeah, so you see that was not that difficult of a question. Now, one thing as we go through, you'll see some of these examples and stuff. Be careful when you start getting like too many zeros in front of a number or something like that. You know, if you're, I'll show you a little trick that I do if you're not sure. Let's say you were comparing, I don't know, how about 0.0050, and then, or 5, anything, doesn't matter. And then if I wrote 0.04 here. Now you got to be careful because obviously 5 is greater than 4, but actually the zero in front, extra zero in front of that 5 makes it a smaller number. Now here's a little trick you can do. You can move the decimal over. You can move it over 4 places, and you might even could do it just 3 or whatever. But if you moved it over 4 decimal places on both sides, you can now make it look like this. Oh, now you can clearly see without making a mistake that that's true. That's just, you know, you might not ever need to do that, but it's potentially a helpful hint for you. So those extra zeros in front, you have to be careful. All right. Okay. Okie doke. Well, that's how we're going to see another method. That's what we're going to do next week. The other method for rejecting hose. We're only going to focus on p-value. In fact, we're going to stop. I'll tell you where we're going to stop here in a second. And then we'll go to the homework, of course. But I mean, content-wise, I'll tell you exactly where we're going to, right here. We're going to stop right before this for as far as new lecture. All right. So like I said, we'll get a little shorter day today and then a little shorter day next week. And this one says find a p-value. And you see I did the calc. Oh, I went ahead and put the 2 right in front. Earlier when I did this, I made the calculation and then multiplied by 2, which was obviously correct. But you can even do the 2 in front like this. Because it's two-tailed, only for two-tailed. I know we need to get some examples here that aren't two-tailed. I just focus on that one because it's the trickiest one of the bunch. If it's left-tailed or right-tailed, you don't have to multiply it by 2. So like I said, whether it's negative or positive, if you're using the chart, you would just look up the negative, 1.72. I'll skip the chart part. But it's 0.427. Multiply that by 2. It's 0.0854. Now we're going to determine whether or not to reject the hoe based on whatever level of significance the problem gives us. Now suppose that the level of significance alpha is 0.05. So I'd put the p-value here on the left, 0.0854. I'll put the alpha 0.05 on the right. And I think it's safe to say that 0.0854 is greater than 0.05. So when p-value is greater than alpha, we fail to reject the hoe. Now suppose they decided they want an alpha 0.10. That's a little different. If the alpha is 0.10, we would say 0.0854, and you don't have to have the equal there, but I included it. I could just say less than 0.10. We would reject the hoe. Now this I was mentioning right here that that's not your concern, but this would not be an ideal result for a statistician. If they're looking for they're thinking they're going to get reject, in favor of the alternative, they want that p-value to be a really, really small number, which is not uncommon. You'd be really, really small. That way you're going to reject no matter what the alpha is. You hate to be totally dependent upon what this alpha is. So I wouldn't feel all that great about this conclusion if I was running this test. And p-values are basically probabilities, so they're always between 0 and 1. Now alphas are going to be between 0 and 1 too, but yeah, or if you thought it wasn't going to be rejected, maybe if let's say if that p-value would have been like 0.2854, okay, then that's going to be pretty much greater than any standard alpha you'd use, so it would clearly be fail to reject. So they'd like for it to be clearly fail to reject or clearly reject, not kind of in this vague area. But this obviously is an excellent example to show you, and it's something you might run across on an exam. We got a question coming up here in a minute that's similar to that idea, where we take a p-value and we take like 3 different alphas and we determine, well, which of these would you reject and which ones would you not reject. So it's an excellent conceptual idea. And they're just reminding us, low p-values. Low p-values is what causes rejection. And I like this. This might have come from the book before this one. Might not even come from this book, but I like this saying. If the p-value is low, then the hoe must go. Bye, hoe. So p is low, the hoe must go. Yeah, so very tiny p-values lead to clear rejections. Okay. Now this test statistic might look somewhat familiar. It's not exactly the same because we're using the mu0 thing here, but that looks like, how we calculated our z value whenever we were doing problems, under the central limit theorem. Remember, I had to take the standard deviation. Oh, that's coming up. That'll be on this test too, won't it? Yeah. I keep forgetting that wasn't on the last test. That's actually on exam 3. So okay. But so means you'll be doing this on exam 3 also, which is fine. All right. And the test statistic Z is you take your sample mean, you subtract the mu0. The technical term for that mu0 is the hypothesized mean. That just indicates the value you're testing against, in other words. And then your standard deviation divided by the square root of n. Now there's 2 ways to do this. P-values and then using rejection regions and critical values. I'd say that p-values is the most common way to do it, but it's especially with technology. But we need to look at the other way to do it too. So using p-values, and we'll see the technology come in here in a minute. See the calculator come in. Okay, one of your distributors reports an average of 150 sales per day for the distributorship. You suspect this average is not correct, so you select 35 days and determine the number of sales each day. The sample mean is 143 daily sales with a population standard deviation of 15. So that indicates we're using the Z because of the population. Given a level of significance, is there enough evidence to doubt the distributor's reported average? All right, reports an average of. Of, as I mentioned earlier in the last section, is like is. Of and is both mean equal. So let's look at our ho and ha here. Here I just wrote down all the pertinent information that was given in the problem. But the ho and ha, there we go. Equals, not equals. This is a little tricky. The way you think about this, why is the claim the alternative? See, the distributor is reporting the average of 150, but you're the one doing this test, so you're the one saying this is not correct. So you are making this claim right here. We're not going by based on what the distributor says. But naturally, if you're claiming not equal to 150, then for sure that means a mean equals 150. So it's a little tricky there just on where the word claim goes. But the ho and ha is pretty straightforward, that it's equal, not equal. This is the two-tailed test. Now, okay, so like I said, I'm gonna show you how to do the Z-test in the calculator. But here's the setup, just using, well, this is using a calculator, but you know what I mean. We're gonna walk through it as if you're just using a scientific calculator. So you take 143, which is your X bar, right there from this formula. The mu zero, what you're testing, is 150. And then your standard deviation is 15, and then n was 35. We selected 35 days. So it's 15 divided by the square root of 35. And just using a regular scientific calculator, you get negative 2.76. And once again, I'm only mentioning the multiply by 2 for two-tailed test. I mean, we're going to see some left and right tail tests coming up, but I kind of regret that I haven't already done one because we're only seeing this. It kind of gets this doubling thing pushed in your brain here, but it's only double for equal, not equal. Now we have negative 2.76. You can look that up on the chart, or you see I did the normal. That's back when I used to use negative 100 instead of negative 1e to the 99. You should still use the negative 1e to the 99. Didn't hurt anything, but so, or the chart 0029, multiply that by 2, you get 0058. So there's your p-value on the left. You put your alpha, which that's always given in the problem, 0.01 on the right. I have a less than there, but notice this is, you got to be careful with this one, like I showed you that other example I just made up, whatever. So you might, the 5, you might think, ooh, 5 is bigger than 1, but the extra 0 makes it a smaller number. If you do the little trick about moving the decimals over, you would get 58 on the left side, and you would get 100 on the right side. And then you can clearly see that 58 is less than 100. So it's less than, so we reject the whole. Now here's some of this wording we're going to start getting used to a little bit too in problems. So that means the claim was the alternative. So that means we're supporting the alternative. Yeah, the claim is not always the alternative. It just is in this problem. So that means we have sufficient evidence to support the claim because we rejected the whole to get to that claim, that the mean sales per day is not 150. We feel pretty strong that that's true. So you got to be careful on the wording on this, because the only time that you're going to be supporting the claim is that the claim is the alternative and you rejected the whole. All right. Now here's the sort of the setup here, and I'll walk through it in the calculator also, but that'll stay right there for you. I did this using an older calculator, but it won't make that much difference. Stat, test. Okay, last week we used number 7 and 8. Today and next week we're going to use 1 and 2. I've had people get these confused, but it's not that big a deal. Just think of it this way. 7 and 8 have the word interval in it. That means confidence interval. 1 and 2 have the word test in it. That means hypothesis test. Because back when I've done face-to-face classes, and I will be again starting in the spring, is people will come up after class and this doesn't look right, and they'll be trying to do a Z interval, but they're using Z test or vice versa, so they recognize that the input doesn't look right. That's because they picked the wrong thing. Not just the difference between Z and T. I mean the difference between choosing test versus interval. But if you just think of it the way I just said it, it's pretty straightforward. Test for hypothesis test, interval for confidence interval. Enter. Now, the value we were testing against, I believe, was 150. Standard deviation is 15. means 143, N was 35. Now, there's something I just want to point out. You may not have noticed this, or it's not important, certainly, but I mean, you might look at this and go, hey, if we're saying it equals 150 and we got a sample mean of 143, does that automatically end it right there because the sample mean doesn't equal the mean we're testing against? No, it takes everything into consideration here. It's not just that number alone. It involves the standard deviation, it involves the N, it involves the level of significance. So it's not just straightforward as doing that. In other words, in this case, we did reject, but that wasn't the reason because this number was 143. But so it just takes everything into play here. So that's all right. You don't have to worry about that. Now, this is very important right here, especially to get the p-value right. It would get the test statistic right no matter what you pick. Now, what the next line gives us, it only gives us the ha's. It doesn't have to give us the ho's. It only has to give us one of them. It gives us the 3 possible ha's for our problem, alternatives. We have to choose the correct one. Now, our problem, and see I wrote right there the ha's, our ha is equal. So we want the one that's equal is the one that's already highlighted. If you didn't want that one, I'll show you. You could just, you move over and hit enter, pick one of the other ones. We want that one right there. I don't care about this color business. And there we go. And then the P, it gives you your test statistic, which is negative 2.76. And then there's your p-value right there, 0.0058. Now, these answers might be a little bit off, like we've talked about before with normal stuff, because it's versus someone using the chart or even answers on a test. It might be a little bit off because it's going to do this more precisely. See, when we're using the chart, we always round our Z to 2 decimal places, but the calculator will use all those decimal places. So this p-value might be a little off, but not, like I said, but I think it should be okay in the homework, though, no matter which way you do it. I think it's set up for chart answer or calculator answer, even if they're a little bit off. But it doesn't mean something was done wrong. It just, the calculator does it more precisely. All right. Ta-da! How about that one? Wasn't that exciting? Let me look again. We got a couple of these, All right. Sprinkler systems. Activating temperature is at least 135. To test this claim, you select 32 systems and find the mean activation temps 133 Fahrenheit. Population standard deviation of 3.3. Given a level of significance of 0.10, do you have enough evidence to reject the manufacturer's claim? All righty. Let's look at the ho and the ha. At least 135. At least symbolically means greater than or equal to. And because it has an equal, it is a ho. So you would have greater than or equal to, that's what they're claiming. And then what pairs up with greater than or equal to would be less than. Now notice this one's saying rejecting the claim. Like, yeah, you can only support a claim if it's the ha, but you can reject a claim if it's the ho. Remember, you can never support the null hypothesis. You can only reject it. All right. Now, so I just kind of wrote down all the pertinent numbers here. Now, this one, by definition's a left-tailed test. So if you're using this formula, you would go 133 minus 135 over 3.3 divided by root 32, and I get negative 3.43. I didn't put that in the calculator, but if you did, I think you can get it. If you just be careful, notice how I use the parentheses. That's important. So if you look up negative 3.43 on the chart, you'll get 0, 0, 3 right there. And that's the p-value 0, 0, 0, 3. And the alpha is 0.10. So since 0, 0, 0, 3 is less than 0.10, we reject the claim that the activating temp is at least 135 degrees. We reject that. In other words, we're kind of suspecting it's a little bit lower. Okay, we rejected the claim because that means we reject the hoe. I may skip the calculator on this one because I say you're going to see me do calculator in the homework here shortly. So, but let me just show you, everything's kind of the same, but right there, look where I got the red arrow right there. Because look at that, you see the ha right there. You have to slide over for this problem and pick the less than for the ha. Now, sometimes these p-values are going to be so small that the calculator is going to show it in scientific calculation. So that e -4 just means you move it over 4 decimal places to the left. So if you take that dot and move it 4 to the left, you'd have 3 zeros in front of it. So there's your 0.0003. So yeah, you'll see that sometimes whenever they're tiny p-values like that. And then there we go. Pretty exciting. All right, 85 8th grade students has a mean score of 282 and a population standard deviation of 35 on some national math assessment test. The test results prompts the state school administrator to claim or declare, same as claim, that the mean score for the 8th graders on the exam is more than 275 without, calculating every exact score. Who knows? Maybe he or she gets a new swimming pool as a bonus or something if they achieve a certain level. I don't know. Probably not, but I'm just kidding. But I guess you never know. So they're claiming it's more than 75. Given a level of significance of 0.04, is there enough evidence to support the administrator's claim? That tells you the claim will have to be the alternative. And it is, because it's more than. More than is always a ha, because it doesn't have the equal. It pairs up with less than or equal. And then that's the claim. So if we're going to support that claim, that means the hoe has to be rejected. If we don't reject the hoe, we don't support that claim. That is a right-tailed test. So I did it as a normal CDF. Yeah, these, if you're doing them with charts or whatever, like the last one and then this one, you don't double your answers for these. You just look them up as negative. So here are the important values from the problem. You calculate the Z, which I did right there. You get 1.84. But here's kind of a picture of what a right-tailed test looks like. But to get the area under the normal curve, we use the symmetry process that we've learned before. We would flip it over and look up negative 1.84, and that gives me 0.329. That's, you can do it that way. And it's not, you don't double this one. Now, since 0.329 is less than 0.04, not much. I wouldn't be real overly boastful about this result, but I guess, but by technically it does satisfy it. P-value less than alpha. Therefore, we reject the hoe and we support the administrator's claim that the mean test score is greater than 275. This is just fantastic here. This one's, if I remember correctly, this one's kind of weird. I don't think I would try to, like I said, I don't want to try to trick you too much on the wording here. Coin operated laundry, last 5 years, revenue was 675. Yeah, we don't even need all that other data because we're not calculating anything here. I don't think. Yeah, because it's telling you it's decided, you know, right here. Get that bar out of my way there. Yeah, so it's already reached the conclusion for us. So mean revenue was 675. Well, okay, I guess was is kind of the past tense of is, so we can just kind of go with that. Oh, ha, equal, not equal. We did not reject. And let's see, the owner claims, okay, they're claiming this. And we're not rejecting. So not rejecting doesn't mean we 100% agree with it. We just can't say that it's wrong. So here's where the wording has got to be careful with all these negatives in the wording there. And then let's look at answer C, and I explain why that's right. Okay, it says there's not enough evidence to conclude that the mean was not 675. In other words, we don't have the evidence to say that this is true here. We don't have the, so notice nowhere does it say it's agreeing with the 675, but we cannot disagree with it. So there's not enough evidence to conclude that the not equal is true, in other words. Kind of a lot of word games here, isn't it? Okay, that's all there is to that one. Let's do this one, then we're going to go to the homework. Yeah, this is, okay, the way this, here's how I show you, here's how I would just sort of do this. Gives you the p-value, and it gives you 3 different ones, and you just got to answer yes, yes, no, no, yes, yes, based on each of the values. So here's what I would do. It's the same p-value, so I would just go, and we're testing 3 different ones. I'll put that, that's going to be the same thing on the left every time. And I'll go in order, 0.10, 0.05, 0.01. Now what I'm going to do is I'm going to put the proper inequality symbol here. 0.36, 0.10, I'm going with less than right there. 0.36 and 0.05, I'm going to go with less than again. Now, how about 0.36 and 0.1? Now I'm going to go greater than. So let's look at that for a second and see if you're okay with that. And we know that less than means reject. P-value less than alpha means reject. So the first one is yes, yes meaning reject. The second one is yes meaning reject. The last one would be no, not reject. So we're looking for the answer that says yes, yes, no. And that is answer D. I could see first looking at this might be would have been a little confusing. Hopefully after seeing the explanation that it's not as bad. All right, we're at the stopping point lecture-wise. We're going to take a peek at the homework. Now the homework, all right, so we did that. I'll exit out of this. It's going to have, the problem is it's going to have, each problem is going to have multiple parts where it mixes in what we just learned and what we didn't learn. So I'm probably going to have to just show the completed problem and then work to the answer, in other words. And then after we learn next week's stuff, we can do the entire thing. You'll see what I mean here in just a second. Yeah, because I'm splitting up 9.2 for lecture purposes, but the notes, and nor should the homework split it up either. It's fine as is. Oh, well, okay, this is the, I did it, this problem, okay. This problem is included here, but it's also included in 9.1. That's weird, isn't it? Now it looks like it just means I need to, so I must have just moved this one or copy this one and didn't get rid of the other one. Huh, that's weird. Maybe I should get rid of the other one. Because here it is again. 1034.02. 1034 is greater than 0.02. P-value greater than alpha means do not reject. Okay, p-value lower tail means left tail. Okay, if this book might use that terminology, that's okay. Lower tail is left tail, upper tail is right tail. So negative 2.12, and it's this one we don't double because it's left tail, or right tail you don't double, only two tail. Negative 2.12. How about 0.170? Let's see. Dang, I keep going wrong. 0.170. Okay. Okay, this would actually be good because I don't have to do part of a problem that way. Of course, it kind of gives you, it's pretty helpful, and it gives you the ho already, or ho and ha. Yeah, like one of these where you got to determine the ho and the ha. But these are the ones that have the parts, like I said, that's going to have stuff from the rest of this section. Well, let me go back and do one of those two. I'll need to do both of those, and I'll jump over to one of these. The second and the third one, I believe it was. No, third and what was number one? Oh, we did that, yeah. So I'll either do 3 or 4. It makes no difference. All right, I'm tired of two tails. Let's do this one. So let me just slap it right in the z-test. That'll make life easy here. Yeah, and anytime the ho and the ha is already set up, that really, because like I said, a lot of the thinking is involved from, reading the statement and setting up the ho and the ha, like those other problems coming up. Okie dokie, let's go. Stat, clear, z test. Stats. All right, so I'll just toggle back and forth here. The mu0 that we're testing against is 53. All right. Standard deviation is 13. Sample mean is 55. N is 32. Now we have to pick the right symbol here. It's going to be whatever the ha is. All right, well, okay, H1, the alternative. Yeah, ha or H1, whichever one. Greater than, you see that? The alternative is greater than. So I want to pick the greater than symbol. Hit enter, so it'll accept it. Look at that. Greater than. And I believe it wanted test statistic. Let's see. 2 decimals, 0.87. Yeah, okay, this is what we don't know yet. Dang it. Well, all right, let me go back here. You see there's the p-value right there, 192, blah, blah, blah. If I hit show completed problem, hopefully it won't change the numbers on me. I thought it was only going to, because it didn't indicate it was going to ask me this stuff by the wording of the original problem there. Come on, keep the same numbers for me. Boo! Yeah, see, I should have done it. I mean, I could do it for this one real quick, but I'll just go a little faster this time. But I guess so now you'll see everything. But I guess I didn't know that was going to be there. I thought we could answer it, fresh there or whatever. But all right, so 45 we're testing against. Yeah, should have done that before I started. Totally my screw up there. All right, page vaporized there. Oh, there it is. 45, 48, 12, 34. $48, 12, not in that order, 34. There we go. I just remember which one. There we go. So this one's also a greater than. Same kind of, well, same problem, just new numbers. There's the test statistic, 1.46. Why does it take so long? Why does it keep doing this to me every time I come back over there? This is getting annoying. Now it's taking even longer. If I move away from it, though, it's going to not be good here. Oh. Okay, let's see if 0.72 is correct for the p-value. Yep, there it is, 0.72. Beautiful. There we go. Now, actually, we'll learn this stuff next week, but let's incorporate what we know today as far as rejecting or not rejecting. It's going to be the same answer. You got to get the same answer by no matter what method you do. But here's how we would look at it based on what we know right now. 0.072 is greater than your alpha of 0.01, so we do not reject, which is what they have there is do not reject. They're just doing it by something we haven't learned yet. But do not reject is correct. All right, let's jump ahead here and go to one of these other ones. I'm going to have to just bring up all the answers. Although I could probably do we can do the first part, and then I can bring up the whole, and then it's okay if it brings up new numbers. Students advertise classes of 36 or less. That's what they're claiming, and that's what we're testing. So the university's claiming that 36 or less. I like 36 or less being the same thing as less than or equal to. And less than or equal to would be a ho. That pairs up with greater than as its ha. Excellent. But now I'm going to go ahead and undo this. So we can skip over the stuff that, see the critical Z-score, that's next week. But we can get the test statistic, we can get the p-value, and then we can decide if our the reject matches that reject. And it will, but I can explain why it does. All righty, so let's put in the data here. So now it's 33 instead of 36. That's fine. Stat, edit. Nope. Brain fart. Stat, test. $33, I think. does it keep doing this to me? Oh, I have to hit the screen. 33. Now I get it. I have to tap on the screen to bring it back. Seems weird, but 42 is N. 36.8 is the sample mean. Standard deviation is 8. 42, 36, 8, and 8. That's 8. No, 36.8. And N is 42. Yeah, I better double check that. All right. I think we're good. Oh, we need to check greater than is the alternative. So I have to make sure I pick the greater than. Okay, it's already defaulted from before, but the greater than is there. Let's hit calculate. The test statistic should be about 3.08, and the p-value is 0.010. I think they only asked for 3 decimal places. 0.001. Let's see how we did. There it is. 308 and then 0.001. That's correct. Now this says reject, and then how we would do reject is we would have to bring in the alpha right there, 0.10. Well, 0.001 is definitely less than 0.10. So it's reject. All right, we'll do at least one more of these. Let me look and see if there's anything really weird. Well, of course, anything really weird, I can tackle the entire problem next week, because then we can just do the whole thing, because we'll know the other part. So I'm just going to look ahead here just to see. I might do that one. I like the 927. They all look pretty much the same. Okay. All right, this will work. Pizza place claims the average delivery time for orders is under 44 minutes. Okay, under, that pretty much implies less than. We'll just look at the ho and the ha to make sure you're okay with that. Under 44 minutes, less, which is less than. Less than has to be a ha, and then it automatically pairs up with greater than or equal to. So we got a left-tailed test here, which means the test statistic is going to be negative. You didn't have to know that, but it will be. So now we can just put the numbers in there. And we're looking to see if we get this negative 2.22, and then if we get 0.013. All right, so 44, 42. Okay, stat, test, Z test. Yeah. N was 42. It's already still 42. And let's see what the mean and standard deviation were. 40.5 and 10.2. All right, let's just double check to make sure I got that right. All righty. Now notice that on our hypothesis test, the alternative is less than. All right, so we have to pick less than the calculator. So now hit enter. We've now selected less than. And then there it is, negative 2.22. I believe 0.013 was correct. And 0.013. And they're saying by the other method they got reject. We would also get reject because 0.013 is less than 0.05. So p-value less than alpha, we reject. All right, I guess we can pop out one more of these till we see this again next week. Let's see. I don't know. Coffee, I don't think we did the coffee one. Did that one. All right. We'll do the coffee one, that'll be it. Coffee industry claims the average adult drinks 1.8 cups of coffee per day. Okay, so you never want to try to read too much into these. You know, the fact it's not saying anything about more than that or less than that, don't try to infer too much. It's pretty much an equal. They're saying that's the amount, you know, that's why it'll be an equal and a not equal. So we selected 50 people, and the average of those 50 was 1.95. Standard deviation. Okay, let's see what we get here. $1.8. That was 1.9. Oh, no, that's 1.95. Go back, and now I need the N and the standard deviation. The N is 50 cups. Standard deviation is 0.4. All right. So okay, this is an equal, not equal. So very important we select that. And I see a Z of 2.65 and then a P of 0.008. How'd we do? 2.65, 008. And here's one of these deals, you know, with the extra zero in front of it. 008 is less than 0.5 because of that extra zero in front. So we reject. That's exactly what they have right there, is reject. So that's tremendous. I thought what I'd do to conclude the show here, of course, I'll, you know, be around for questions and stuff, but I think I promised last time, or promised something, or either an announcement, that I'd kind of just take a quick peek at that assignment thing, Excel assignment, if you'd like to take a quick look at that. I'm not going to spend a long time on it right now, but I can just sort of verbally walk through some of the highlights, and then you can always go back and watch this later, you know, listen to it again, or at least this part of it if you need to. So if that's okay with you, I think I'll do that. And then, like I said, then we'll get to your questions that you may have. So I don't have the actual assignment ready in Blackboard yet, but I can't imagine anybody's already ready to submit all their answers. So I think I'm okay. I think I got a little time there, but you can be playing around with it. A lot of it's pretty easy, I think, especially the ones where it just tells you what commands to do. So I'll bring up the Excel file that goes with it too. So one thing I want to make clear is that all you're doing, some people ask me, do we have to submit the spreadsheet or do we have to do this or that? No, all you do is bubble your answers in Blackboard. That's it. That is it. So there's what the spreadsheet, and the nice thing about this is if you do something up and you mess up the spreadsheet or something, just go back and get it again from Blackboard, whatever. So you don't have to worry about protecting it or whatever. You can just go get it fresh right out of Blackboard. All right. Just 3 sets. I didn't label these other data as having any kind of meaning or anything. Maybe one of these days I'll do something and give it a title or something, but no effect on what we're doing though. Oh. All right. First two, average, standard deviation, .s. It doesn't get any simpler than that, I don't think. It was 200 of them, so it'd be A1 to A200. So you'll use that mean and standard deviation to create 3 intervals, which would be 3, 5, and 7, actually. So I'll tell you 4 and 3, 5, and you calculate, you do plus and minus 1 standard deviation, plus and minus 2 standard deviations, plus and minus 3 standard deviations. I think if you refer back to the notes on empirical rule, that should make it easy to guide you right through this. So you're creating the data. Now this part, and I showed this, I didn't put this on a test or anything, nor would I ever put this on a test. I didn't, I said I wouldn't. We did this where you can, how to figure out, you sort them, and then you figure out how many numbers fit in your interval. I showed that one example in my notes where I'd already kind of done it. Now I won't use this answer per se, but let me show you what I mean. I'll sort this, and I'll just make up 2 numbers, lowest to highest. So I'll say between 80 and 110. You see, that wasn't one of the answer choices in the problem before. But so you have to get that right, and then you have to highlight. And the way I did that was I'd go and pick the first one that was at least 80. You don't round up to it. So I would not use the 79.96. I would use this one right here. Then I would highlight to where I did not go over 110. Right there. And then you count how many of those, but counting is real easy because you go down here in Excel and it tells you the count. So it tells you there was 104. So then what you would do is after you did that count is come up with this percentage. So obviously that's none of these are the right answer. What did I say? That was 104, was that? So you take 104 and divide it by 200, and you would have, if that would have been right, which it isn't, then you would have been looking for 52% as your answer here. So you're just taking the amount of values that fit in that so you got to get the interval correct from number 3, and then you look and see how many fit in there, divide it by 200, and that gives you the answer. So what I'm trying to do here is just like I did in that example in the notes, I'm just trying to test for this data set how close, does this data relate to the empirical rule. You see the percentages are all in the 60s somewhere because we're expecting it to be close to 68. Then all you do, that's 3 and 4. Then 5, you just do plus and minus 2 standard deviations to get your new interval, 95. You sort and highlight that column, and you see these percentages are all hovering around 95. You divide that total by 200. Then you do it again for 99.7. And then same thing here, all the values that fit in the whichever one's the correct interval from up here. You count them all up, divide by 200, and obviously you're expecting this one to be, really high, close to 100%, or maybe even 100%. That's certainly not uncommon for it to be 100% for the third part of the empirical rule. So that's it for those 8. Here's another average command. There's 9, another standard deviation, just for new data. It's the data in column D. That's easy. Now, I guess some of this, if you feel like you can just do it in the calculator, go ahead and use a T interval process in the calculator. But this is showing how to get, using technology to get what the critical value. Actually, though, you probably do need to do this, though, to be able to answer 11, to do this command right here. So it's a simple command in Excel. It's just equal TINV. You're getting the value. That on the T distribution chart, we only use those select values for T because it takes technology to get anything other than that. The Z is a little bit different. If you go back, the process for the Z, it's not that hard to come up with 74 percentile, or not percentile, 74% confidence level. That's just using the normal curve. That's not difficult. But this would not really be doable without technology. I guess if you have the 84 or higher, you could use that inverse T command I showed in the notes. But heck, I would just do this. So I think we have 20 values, don't we? I think that list has 20 values. So you would just do equal T invert INV. For this one, you would just do 1 minus 0.75. Easy peasy. Because the 19 is the degrees, you have to put the degrees of freedom in there. So like if I just put this one in there and show you, this isn't the right one, but just pick somewhere, whatever. You're just getting the critical value. It's not based on data, but I can go equal T inverse. I can do that same one. 1 minus, you do 1 minus. 1 minus 0.96. Comma 19. And then it's going to give you that, whatever that critical value is. All right, but that was not the right answer for this problem. So you do that. But here's what I was talking about, where you could probably just go ahead and use the calculator. You don't have to actually you have to get this number, but you don't have to use it, because you can let the calculator do it internally if you want to do that. You can just do the 75% T interval basically if you want to, because you're going to have 9 and 10 are going to be your mean and standard deviation. And you don't even really need number 11. You need 11 if you're using the formula, but you don't in the calculator. All you got to do is tell it the confidence level. So you wouldn't need it to do it. That's only for folks that were not using the fancy calculator. So same thing here. You do it for 85, you get this number, but then you can just do the 85% confidence interval. Oh, crud, there's a typo. Dang it. I got to make an announcement about that. I knew there'd be one somewhere. This one should say 9, 10, and 13, not 11. Because, okay, I need to fix that and make an announcement too. That should be using this number. The other one was correct when it said 9, 10, and 11, because it's using the problem. Okay, that should have said 9, 10, and 13. Okay, I need to fix that. Or I could just or use the calculator or whatever. But now, it's not a problem for you if you're just going to do this in the calculator. Takes care of that. Now, we just started the Hos and Haas today, so and we haven't done the critical values yet. So really, you could probably do number 15 without any further assistance. 16 will be based on next week. 17 you could actually do now. 18, I guess you could use p-values and do that. But after next week, we'll be able to clearly do one of those. So in fact, if you look at number 15, based on what we learned today about where the ho and ha's and what symbols they have to be, I bet you'll be able to identify 2 of those answers are impossible. I mean impossible without even reading the problem because of how the symbols are written. I bet you can see which ones they are, right? So that narrows it down to only 2 choices. So because the ho has to have the equal, right? So I just put those in there, see if anybody would pick them. So there's those 4. And then the last 2 is based on that linear regression stuff we learned a long time ago. So you can go back and look at the notes and see how to do that. You can get the slope and the intercept. I'm trying to remember, when you go back and look at that, I think you have to be careful. That's the one where you have to be careful that maybe the y's go first before the x's. I'm trying to remember. But anyway, just go back and look that up in the notes. It's one of them you had to put it was important to put the y values in first. Might be for both of those. But then you get the slope, you get the intercept, and you can get the regression equation right there. And then 20 is super easy because all you do is get the equation right for number 19 and just plug in 5.5 into whichever one's the right equation. And then you'll have it. And then that's it for the Excel assignment. That's it. Done. So I don't think it's too bad. All right. So with that being said, I think that I'm going to keep this part in the lecture video, but then other stuff you ask me afterwards, I just always delete that part. But I'm definitely going to keep this in there for everybody to see.